Yeah, welcome back. In this topic, we are going to be looking at what we call the Ethernet trunk, iStack, and CSS. So I will read the forward. As services develop and the campus network scale expands, users have increasingly demanding requirements on the network bandwidth and reliability. Bandwidth and reliability. Traditional solutions improve network bandwidth by upgrading devices. You upgrade a device, or you implement high reliability by deploying redundant links and using STP to avoid loops. This leads to low flexibility. It's time consuming to configure and troubleshoot complex configuration. So those are the disadvantages of the traditional solutions. In order to improve bandwidth, you have to upgrade devices. Implement high reliability, you deploy redundant links and use STP. Low flexibility disadvantage, time consuming to troubleshoot, and complex configuration. So we're going to see how when we learn about Eth Trunk, iStack, and CSS. So this chapter will describe these three technologies. iStack is intelligent stack. CSS is cluster switch system. And these technologies will be used to improve network bandwidth and network reliability. By the end of this chapter, you should be able to. Maurice, please help us.
By the end of this chapter, you should be able to, 1, understand the function of link aggregation. Number 2, you'll be able to understand the link aggregation types. Number 3, you'll be able to understand the link aggregation negotiation processes in link aggregation control protocol, the LACP mode. The second last is that you'll be able to understand the advantages and principles of iStack and CSS. The last point is that you'll be able to understand the common applications and network of link aggregation and stacking technologies.
Wonderful. Okay. So let's do this. So let's begin by looking at network reliability requirements. So what is network reliability? Network reliability refers to the capability of ensuring non-stop network services. Non-stop network services. When a single point or even multiple points of failure occur on a device or a link. So non-stop services. Yes, there's a problem. Failure has occurred on our network, but the network is still able to serve people. Now, network reliability can be implemented in one of three places, what we call cards, or the device, or the link. Network reliability. Network reliability, you can say points. So you can implement card level, or device level, or link level. Now, why do you think it's important to ensure a high network reliability, non-stop network services on today's networks? Why do you think it's important to ensure high network reliability? That is, even if we have failure in our network, the network will still be able to survive and serve the people. Why do you think it's important to ensure a high, yes, Anthony? Yeah. To avoid economic losses due to service interruption. Because when services are interrupted, then the organization might not be able to achieve the objective. The other thing is that more and more services are relying on the network today. For example, we have IP phones. Most organizations highly rely on these phones. And if your network is down for, let's say, even 10 minutes, it means that people cannot be able to communicate within your organization. The network is also being used to support meetings through virtual conferences. So if your network is down again, meetings are disrupted, and so on and so on. So more and more services, other than just accessing the internet, more and more services within organizations now rely on the network. That's why it's important that you ensure that your network has high reliability. Now, card reliability. Let's have a look at this card reliability. Now, a modular switch. Normally, we have what we call a modular switch and a fixed switch. The switch that I showed you is a fixed switch. Most of the time, fixed switches are used in campus networks, while modular switches are used in data center networks because they provide high reliability. Why are they called modular? Because they consist of different parts like the chassis, power modules, fan modules, main processing units, MPU, the switch fabric or SFU, and also the line processing units. Now, all these parts can be able to be, we have more than one of it, and they can be able to be exchanged or replaced while the switch is still functioning. So the chassis provides the slots for various cards. So the chassis, you can think of the chassis really as this system case. This frame that is holding the entire switch is what you're calling the chassis, the entire of that. So it provides slots for various cards and modules to implement inter-card communication. The power module provides power supply to the device. So you can see that we have several power modules here. There are several. Given this one and this one, they're power modules. So if one power module goes down, there's another one that is still functioning. So that is what you're calling card reliability. Fan module is used for heat dispensation, and it's also very important. Let me see. Where do we have the fan module here? MPU, mounting brackets. Where are the fans?
Can I help teacher locate one?
Yes, please.
Yeah. In the mounting bracket, where we've got the power modules, in each and every power module, we've got at least one or two fans. Then at the right at the top of where you put the first arrow, there's by design on the frame, on the chassis frame, actually, there's always two at the top facing downwards.
Oh, yeah. One here and one here.
Yes.
Okay. Thank you very much. Yeah, so fan module, very important for heat dispensation. So we're going to have several of that. Then MPU, or main processing unit, is responsible for the control plane and management plane of the entire device. Maybe I can just mention this because you'll be hearing of control plane, you'll be hearing of data plane, or forwarding plane. You can also hear of management plane. So control plane is really used with a calculation of, for example, routes. So you remember, for example, we said that like for example, OSPF, the way it calculates the shortest path tree. So it's the control plane that does that. Then forwarding plane will now forward the data from the routing table. So data forwarding, this one simply does data forwarding. Management plane, on the other hand, will assist in monitoring and configuring the device. So you'll be hearing of these three once in a while. Okay, so the other one here is SFU. SFU is the switch fabric unit, is responsible for the data plane. So for forwarding data. Data plane provides high-speed non-blocking data channels for data switching between modules. Then LPU provides data forwarding functions on the physical device. So on the physical layer, really. So that's what LPU does on the physical layer. Provides optical and electrical interfaces of different traits. So normally each of those are normally what we call hot swappable. Hot swappable means you can be able to replace a faulty module without the need to shut down the device and interrupt services. So you can just plug out and plug in, plug out and plug in without restarting, without the need to restart the device. Okay, so for example, in this switch, it provides 8 LPU slots, 4 SFU slots, 2 MPU slots, and 6 power modules, and 4 fan modules. So a modular switch can be configured with multiple MPUs, SFUs, to ensure device reliability. If an SPU or MPU in a single slot is faulty, the switch can still run properly. That's what we call CAD reliability. After an LPU of a modular switch is damaged, interfaces on the LPU cannot be able to forward data. So these are just examples. The ones that are colored in red here means that a failure has occurred on one of those cards. And if that happens, we still have a backup and the others can be able to work. So you see, for example, for the line processing units, it provides the interfaces. If this card that is providing interfaces has gone down, then these cards are still going to be working. Now, to provide reliability, you can also provide what we call device reliability. Device reliability is done by using redundancy, device redundancy. So in this particular example, we have a network that has no device backup. So for example here, if this aggregation switch goes down, then every other person that is connected to this particular uplink is going to be disconnected, is going to be disconnected at this particular point, and they cannot be able to access the network. Otherwise, it's always important for you to provide device redundancy, especially at the aggregation layer and at the core layer, by providing, for example, more than one device, so that in case one device goes down, then the other device will work. Normally, when we provide device redundancy, like it is in this particular hierarchical architecture, we have to configure the spanning tree protocol in order to prevent loops. But if this device goes down, then this root port is going to we are going to disable this and activate this alternate port, and therefore data now is going to be forwarded via this route in case there is a fault. Okay. Then link reliability. Link reliability is the other way to improve your network reliability. So just having more than one link to avoid what we call the single point of failure. Single point of failure. Single point of failure. So you deploy multiple links. Of course, again, a loop can form here, so you have to deploy STP to prevent loops from occurring. So let's look at the principle and configuration of link aggregation. So link aggregation is when multiple links, okay, when multiple links exist between devices, traffic is forwarded on only one link due to STP. Does that make sense? Does that make sense? We have switch 1 and switch 2, right? And we've interconnected switch 1 and switch 2 with how many links? 1, 2, 3, 4. Now, after we configure STP between S1 and S2, how many links are going to forward data? Just one, right? Just one. Because on the non-root bridge, all the other interfaces other than the root are going to be blocked. They are going to be blocked so that we don't have a loop. So that's the main problem. That's the main problem with STP, for example, that it's going to make all these links idle, while this link is going to be overwhelmed with all the traffic. So are you seeing that problem? So are you, by increasing the number of links between these two switches, are you going to increase the link bandwidth? Yeah? By increasing, if you've deployed STP there, by increasing the number of links, are you improving the link or increasing the link bandwidth? The answer is no, right? Okay. So the solution to that is what we call Eth Trunk. Eth Trunk technology is also called the Ethernet link aggregation technology. It involves bundling multiple physical links into a logical link in order to increase link bandwidth without having to upgrade the hardware. So these interfaces are 1 gigabit Ethernet interfaces, each one of them. So these on 1 gig, these on 1 gig, these on 1 gig, these on 1 gig. Now, if we bundle up these interfaces together to form an Ethernet trunk, then the sum of the individual bandwidth is going to be the bandwidth of this logical interface. So if we add 1 plus 1 plus 1 plus 1, then we have 4 gigabits, 4 gigabit, 4 gig as our new bandwidth for this logical interface. So that's how, simply put, that's how the Ethernet trunk interface works. Combining multiple physical interfaces to a single logical interface. So we want to understand how that is done. Please, let me insist this, that anytime we are talking about gigabit Ethernet interface, for example, or that particular speed, of course, here we mean it can be able to process at 1,000 megabits per second, right? Are we together? So anytime we mention that, we are not referring to the speed at which the link can be able to carry data, but we are referring to the speed at which the interface on the switch here is able to process data. Are you getting the point? Are you getting the difference? Have you been thinking that maybe this 1 gig is the speed of the link? So it's actually the speed of the interface. Are we together? See, when you looked at the switch, you saw that some of them are gigabit Ethernet, some 8 gigabit, some 10, and so on and so forth, right? Yeah, so that speed is the speed of the interface. So what we're saying is that on switch 1, we can bundle up this interface, this interface, this interface, and this one together to form a single pipe. And that pipe, its total bandwidth will be the bandwidth of all the interfaces that we've bundled up together and are in forwarding states. So if each one of them is 1 gigabit, then we're going to have 4 gigabits. Okay. So basic concepts of the Ethernet trunk. Where do I start here? So whenever you add individual interfaces, to an Ethernet trunk, then those interfaces are called, they're called member interfaces. Are we together? They're called member interfaces. Now, the links that are interconnecting the member interfaces, on the other hand, are called member links. Member links. And now, that logical pipe that you've created is called a LAG. LAG is link aggregation group. Link aggregation group. So it's a logical link formed by building several links, by bundling several links. Now, each LAG has one logical interface known as the LAG interface or Eth Trunk interface. So a LAG interface is an Eth Trunk interface. Now, on a LAG or on an Ethernet trunk interface, you might have some links that are forwarding data and other links that are not forwarding data and are just acting as backup. So for example, here, these ones that have blue are forwarding data, and they're referred to as what? Active interfaces, while the others are referred to as inactive interfaces, the ones that are not forwarding data. Now, active interfaces are also referred to as unselected interface. Inactive and select, while active interfaces are referred to as selected interfaces. So for example, when you'll be doing the lab for link aggregation, you'll see that the status of the active links is selected. The status of the inactive links is unselected. Now, the other important thing is what we call the link aggregation mode. So we have two link aggregation modes. So link aggregation modes. So number one, we have the manual mode. Number two, we have the LACP mode. Now, when you manually configure Ethernet trunks on your switch, then that is what we call the manual mode. On the other hand, so that is done by the administrator. On the other hand, if you enable a protocol, this protocol is called link aggregation control protocol. If you enable your switch to create Ethernet trunks using this protocol, LSCP, then that is what we refer to as the LSCP mode. Is that clear? Now, as we continue learning, we are going to see that sometimes or an Ethernet trunk will have an upper and lower threshold number for active interfaces. Especially when you do the lab, there's a part where you're going to test that. Okay. Now, in order for an Ethernet trunk to work, there are parameters that need to match on both ends of the switch, on switch 1 and on switch 2. So the following parameters must be the same for member interfaces in an Eth trunk. So number 1 is the interface rate. By interface rate, we mean the processing speed. So don't add Ethernet, don't add 100 megabits per second interfaces to an Eth trunk that has 1,000 megabits per second. Don't add Ethernet interfaces to gigabit Ethernet interfaces on the same Ethernet trunk. Are we together? So that's what we are saying there. Okay. Number 2 is the duplex mode. Duplex mode. So if all of them are operating on full duplex, so you can't have others operating on full duplex and others operating on half duplex. No. Then the other one is the VLAN configuration. VLAN configurations. On VLAN configurations, we have a number of points. The first one is the interface type. So what that means is access interfaces or trunk or hybrid. So in an Ethernet trunk, all of them are access, or all of them are trunk, or all of them are hybrid. But you can mix. You can mix trunk interfaces and access interfaces in the same Ethernet trunk. The other thing is that for access interfaces, the PVID must be the same. So all of them must be in the same VLAN. The port VLAN ID must be the same. Then for trunk interfaces, must allow same VLANs to pass through. So if on one trunk interface you've enabled VLAN 10 and 20 to pass through, allow pass, then you have to enable that on all the other interfaces that you're going to add on the same. So I hope that is clear. Okay. So let's look at the manual mode. How do you do this? So manual mode means an Ethernet trunk is created manually. Its member interfaces are manually configured. LSCP is not is not used for negotiation between the two systems. So in most cases, look here, this is one of the main difference between LSCP and manual mode. In most cases, all links for the manual mode are in active state. So all links are forwarding data. Are you seeing that here? All links are forwarding data, all of them. If an active link is faulty, lag automatically evenly shares traffic among the remaining active links. So normally all the links will forward data on an equal percentage. So if one link goes down, like this one goes down, then the sharing formula is recalculated and shared equally among the remaining 3 interfaces. If one of the devices at both ends of a lag does not support LSCP, you can use the manual mode. Of course, you know that the challenges of manual mode is that, number one, it increases the maintenance work because you have to create it manually. Then it's not flexible. It cannot be able to respond really to changes. So you only want to use the manual mode if, for example, you're creating an Ethernet trunk between 2 switches and one switch does not support link aggregation control protocol. That's the only time as a network engineer you're allowed to do what? To use the manual mode. Okay, so let's look at some of the problems of the manual mode, defects of the manual mode. So to ensure that Ethernet trunk works properly, ensure that the peer interfaces of all member interfaces in the Ethernet trunk meet the following requirements. Number one, peer interfaces must reside on the same device. Number two, peer interfaces are added on the same Ethernet trunk. So in manual mode, devices do not exchange LSCP packets. Therefore, configurations need to be manually confirmed. So what does this two mean? So it means that the first one here, this one, interfaces reside on the same device. So if you don't have, for example, G004, you don't have an interface called G004 on SW1, you cannot add G004 on this Ethernet trunk. Are you getting the point? So don't make that mistake. Don't make that mistake. If we don't have an interface on your switch, don't add it. That's number one. Number two, you cannot add an interface. The second one here, peer interfaces are added to the same Ethernet trunk. Peer interfaces are added to the same Ethernet trunk. So in this example, you can see we have switch 2 and we have switch 3. So the mistake we've done here is this link, for this Ethernet trunk to work properly, this link is supposed to be connecting to switch 2. Are you seeing that? But we've added this to this Ethernet trunk, this interface to this Ethernet trunk, but it's connected to a different switch. So are you seeing that we're going to forward data incorrectly? We're going to load balance some data and send it to the wrong switch. Are you getting the point? So all the peer interfaces must be added to the same Ethernet trunk and must reside on the same device. So remember that. Okay, so in manual mode again, the device can determine whether the peer interface is working properly based on the physical layer status, based only on the physical layer status. So if this interface goes down, the status will change from up to down, from up to down. So that's the only way it can be able to know. That's the only way it can be able to know that one interface is down. So let's look at the other mode, which is LSCP mode. So with LSCP mode, you're using the link aggregation control protocol to exchange packets between the devices, and they're going to automatically create an Ethernet trunk between them. So in LSCP mode, a link aggregation mode that uses the LSCP protocol, devices exchange LSCP protocol data units. So that's what we are calling LSCPDU, link aggregation control protocol data units, to ensure that the peer interfaces are member interfaces that belong to the same Eth trunk and are on the same device. So an LSCPDU contains the device priority, the MAC address, the interface priority, and the interface number. So we're going to see how those information is used. So this is an example of an LSCP PDU. So you see it has the device priority. The device priority can be configured just like in STP, the device MAC address, the interface priority, which can also be configured, and the interface number. So we'll see how those details are used in the subsequent slides. So let's begin with the system priority. So the number of active interfaces selected by devices at both ends must be consistent. Otherwise, the Ethernet trunk cannot be set up. So in this case, configure one end as the actor. Actor means you're the president. You're the one that will control now the communication, because we want to ensure that the number of active interfaces is the same on both ends. Then the other end selects active interfaces according to who? Now, in LSCP mode, some interfaces can be in active mode while others are in active mode. But who makes the choice of which interfaces are going to be active? The actor. Are we together? Then tells the other, hey, these are the actors, and therefore that one is going to use those ones as the actor. So the actor is determined based on the LSCP system priority. Just like in STP, a device with a smaller LSCP system priority is selected as the actor. Is that clear? Yeah, device with a smaller priority is selected as the actor. Where do we get the LSCP priority? On the LSCPDU, here, device priority. Now, by default, just like in STP, the priority is 32,768. So that is the default. So if you want a certain switch to be preferred as the actor, you configure the LSCP priority to a lower value. The other important concept is the concept of the interface priority. After the actor is selected, both devices select what? Active interfaces on the interface priorities of the actor. So a smaller LSCP interface priority value indicates a higher priority, indicates a higher priority. So as you're going to see in the lab, when you're configuring LSCP, you can use the command, can't remember very well, but something like maximum active, or let me just say maybe minimum active link number, like that. Then maybe you specify 2. So when you do that on an Ethernet trunk and it has 4 links, then only 2 links are going to be selected as active links. Are we together? So how do we select which one becomes active? We select the one that becomes active by comparing their interface priority. Whoever has a lower interface priority is selected as the what? As the active link. By default, the interface priority is 32,768, but it is configurable. Now, by the way, just like in STP, if the default values for the system priority and the interface priority are the same, what do we go to next? On this first instance, if the system priority of all the switches, both of them, if the system priority is the same, 32,768, the default, what do we compare next? The MAC address of the device, right? Yeah, very right, Gadoni. Okay, interface priority, if they are right, if they are the same, the default 32,768, we look at the interface what? The interface number, very well. Smallest in switches, most of the time, the smallest number is the preferred number. Okay, so maximum number of active interfaces. Maximum number of active interfaces. So that means just that. It means just that this value is configured. It's configurable. So when the number of member interfaces exceeds the maximum number of active interfaces, interfaces with higher priorities, that is smaller interface numbers, and smaller interface numbers are selected as active interfaces. So the others will function as backup interfaces or inactive interfaces or unselected interfaces. In addition, links corresponding to active interfaces become active links, and the links corresponding to inactive interfaces become inactive links. So the switch sends and receives packets only through what? Active interfaces. Okay, so what do you think happens when an active link fails? So an active link fails, what happens? This link here, it was an active link, but now it has gone down. What do you think happens? Let's read that together. This one. 1, 2, go. Yeah, inactive link with the highest priority is selected to replace the faulty link. So this ensures that the overall bandwidth does not change and services are not interrupted. And so it provides that that consistency. So active link collection, we won't stay here for so long because I think we've already said it. So normally the switches that have been configured with LSCP mode will exchange LSCPDU. After exchanging the LSCPDU, they're going to look at the maximum number of active interfaces. In this case, it has been set to 2 on both switches. So in this case, switch 1 has a higher priority and will be elected as the actor. So it's going to look at the priority. So in this particular example, actually, the priority is the default, 32,768. But now they'll go ahead and compare the bridge MAC address. So as you can see, these two are the same. The only bit that is not the same is this 5 and 4. So whoever has the lower value, which is switch 1 in this case, is elected as the actor. Okay. So active link election, switch 1 will compare the interface priorities and interface numbers. Interface priorities and interface numbers to select active interfaces. So under the same interface priority, then interfaces 1 and 2 have the smaller interface numbers and are elected as active links. So in this case, again, the interface priorities are the same. We've configured switch 1 and 2 to have a maximum of 2 active links. So it's going to select this one and this one with 1 and 2 because they have lower numbers as active interfaces. So that's how active interfaces are selected. Then switch 1 notifies the peer end of elected interfaces through the LSCPDUs. So when it tells this one, then this one will make the decision to choose these two as active, and it's going to inactivate 3 and 4. So it's going to wait for the actor to inform it. Okay. So that is what we have just said. So in this way, the election is complete. Okay. So let's look at how packets are sent through the individual interfaces on an Ethernet trunk. Now, packets can be sent in one of two ways. The first way is what we call what? Let's read this together. Let's read that aloud. 1, 2, go. And the second one is per flow load balancing. So you really need to understand the difference between these two. Okay, so per packet load balancing is done this way. You see, we have several packets that are coming in. So the Ethernet trunk will forward individual packets on different links on a 50-50 basis. Are we together? Yeah, so just send them. Now, the problem is that if data frames are forwarded on different links, then data frames may arrive at the peer end in a different order in which they were transmitted, resulting to out of order packets. You see, they came in as 1, 2, 3, 4, but they're getting out as 4, 2, 1, 3. Are you seeing that? Out of order because of the different processing speeds and queuing mechanisms and congestion on each of the interface. Are you getting the point? So that's how they can be able to arrive out of order at the end. So that's per packet load balancing. Now, the other one is called per flow. Per flow. Now, in data communication, you'll hear of this term, a data flow. Now, most of the time, data flow is considered as packets that are coming from the same source and going to the same destination. So source IP address, destination IP address, same. Are you getting the point? Or same source MAC address and same source destination MAC address. Are we together? So with per flow load balancing, we want to forward packets that are coming from the same source via the same link. Packets that are coming from the blue PC, we forward all of it from the same, on the same physical link. Are you getting the point? Yeah. So that way we solve the problem of out of order packets. So this ensures that frames of the same flow are transmitted over the same physical link and implement load balancing among the physical links in the Ethernet trunk. So those are the two ways in which we can be able to forward packets on the physical links. So per packet load balancing and per flow load balancing. Okay. The load balancing mode. Okay. Load balancing mode. So an Eth trunk can load balance traffic based on IP address or MAC addresses of packets. That's what I've said. So you can configure different load balancing modes. This load balancing mode will be valid locally only for outgoing packets to distribute data flows to different member interfaces. So do you want to filter based on IP addresses or based on MAC addresses? So traffic can be load balanced based on the source IP, source MAC address, destination IP, or destination MAC address. Or you combine them, source and destination MAC address, source and destination MAC address. You can either use them individually or you combine them. For actual services, you need to configure a proper load balancing based on the traffic characteristic. So if a service traffic parameter changes frequently, it is easier to load balance traffic if you use the load balancing mode used on this frequently changing parameter. So proper load balancing algorithm and improper. So let's try and understand why we are saying this is proper and why we are saying this is improper. So here we have packets that have the same source and destination MAC address, but different source and destination IP addresses. Are you getting the point? They have different source and destination MAC address, but different source and destination IP address. What that means is this. We already looked in the previous topic how data was being routed to the network, right? To the internet. So we saw that example. So what we're saying here is this, source MAC address, it will be the MAC address of the PC. Destination MAC address, it will be the MAC address of the gateway. All the time, by the way. If the PC wants to send something to the internet, source MAC address is the MAC address of the PC, right? Destination MAC address is the MAC address of the gateway, of the interface of the gateway. But this PC has opened up WhatsApp, YouTube, what else? Gmail. So what will happen? It means that the destination IP address will be different. Maybe the source IP address will be the same. So what we are saying here is that source and destination IP address mode, if the destination and source IP are the ones that are changing too frequently, but the MAC address, source and destination is the same, then on this switch, on this Ethernet trunk, you configure which mode? You configure the source and destination IP address mode. So what does that mean? What does that mean? That it's gonna be forwarding, as you can see here, it's gonna be forwarding packets based on the source and the destination IP address. So whatever is changing. So if you're coming and your source and destination, we forward packets now based on not the MAC address, because the MAC address is not changing. We are forwarding now based on the IP address, whatever is changing. So if you have the same IP address, source and destination IP address, then we send you over the same link. Are we together? We send you over the same link if you have the same source and destination IP address. So that is what the blue, red, and black mean here, that we are sending you over the same physical link if you have the same source and IP address. Otherwise, if we had the same scenario, same source and destination MAC address, but different source and IP addresses, so these ones are changing too much, and we use MAC address-based mode. It means because the source and MAC address are the same, we are going to send all these packets via the same physical link. Thereby, we are not going to be load balancing. We're not going to be load balancing because we are going to overwhelm this link while these other links remain idle. Are you getting the point? So it is important that you understand the load balancing mode and which one to configure on which particular instance. Remember, the load balancing mode is configured on the Ethernet trunk. Do you want us to use the source IP or the destination IP, or the source MAC or the destination MAC, or the combination? Source and destination IP, source and destination MAC address. So please have time and try and read the literature behind below this slide in order to understand that better. So let's see the typical application scenario. The typical application scenario of Ethernet trunks. So we can, I love these notes. I love these notes because previously we didn't have these application scenarios, which I think it's very important. And I love Datacom, the way the notes have been designed. It's just much better than the previous routing and switching course. Okay, so the typical application scenario, where do you do Ethernet trunking? So you can do it between switches, or you can do it between the switch and the server. So as we've already learned, normally if you create an Ethernet trunk, you increase bandwidth. We know that, for example, servers are accessed by many people in the network. So we want to increase this bandwidth here so that we cannot have congestion on the interface there and on the interface here. So that's why we want to increase the bandwidth. Otherwise, most of the time, between the access switches and the aggregation switches, you will provide backup links, and it's important that you create an Ethernet trunk between those links. Then between the aggregation layer switch and the core switch, you also create another Ethernet trunk. Now, from this picture, for example, let's just focus here. Do you think we will need to configure STP between this access switch and the aggregation switch? Is there a need for STP? How many say yes? Let me see by a show of hands. Is there a need for STP? Yes. No? Let me see by a show of hands. Okay. Confused? Let me see by a show of hands. Why do we say that we need why do we say that we need to configure STP if we are having a backup link between two switches? We're having these two switches, and we have one link and a backup link. Why do we say that we need to configure STP in this scenario? What is STP used for? To prevent loops, right? So of course here, if a broadcast packet is sent to that switch, it will get its way back via that interface, right? And therefore we'll have a loop, right? So that's why we need to configure STP. But if you bundle this up into a single logical link, then you don't need to configure. You don't need to configure STP because it will be treated as a single interface. So if you bundle them up together, you can think of them as a single interface. So you don't need to configure STP. So please note that a logical interface is just treated like a single physical interface. Right together, even though it contains multiple physical interfaces, but it's treated as a single physical. It's treated as a single interface. Okay. Yes, Luya. Mm-hmm. Mm-hmm. Yes. No, okay. You're saying that the physical characteristics of the switch remains the same, eh? So how are we increasing bandwidth? Remember, the reason as to why we are doing link aggregation, number one, or the impact. Oh, the impact in terms of the processing. Yeah. I get what you're saying. Okay. Anyway, we are doing link aggregation to improve network reliability. Are you together? We are improving network reliability by doing what? Increasing bandwidth. Bandwidth. We increase bandwidth. Number two, we provide what? So we're providing link backup. So Luya is asking, by bundling up the individual links, how does it affect the processing capability of the switch, the overall performance of the switch? Okay, so in my view, this is a personal view, I'm still thinking about how to answer that question, but in my view, the switch will have the processing capability of supporting all the physical interfaces that it comes with. So you bundling them up together will not mean that it will not be able to process those physical interfaces, because it comes with those physical interfaces, so that even if you're connecting to different network segments, for example, it will still be able to support all those interfaces. So it must have the processing capability of supporting all those physical interfaces by design. That is my guess. So bundling them up together into a logical Ethernet trunk will not affect the processing capability of the switch. But of course now the CPU usage will be higher compared to when you've not bundled them up together and some links have been deactivated by STP. Sindio? Yeah, so the CPU memory percentage usage will be higher, maybe 95%. But when you've not used the logical link aggregation, maybe they'll be at 95, 80%, for example. Okay.
Can I also add something, teacher?
Yes, please.
Yeah. By bundling them up, also maybe doesn't affect, doesn't have any effect on the processing speed unless the processor itself the same way you've explained, or unless you are also changing the interface card maybe to a lower version or to a lower output value. Should I put it that way?
Okay, just come up again. Sorry, I didn't hear you very well.
Yeah. Apart from what you just said in terms of
Yes.
the processing speed,
Yes.
unless you are also changing the interface. In this case, maybe you're changing the output interface, which is the NIC, maybe if it's a PC or if it's a switch.
Yes.
If you are changing from a higher version to a lower version, that's when it will also affect. If you're not changing, still the
Okay.
same.
Okay. Sawa sawa. Thank you. Thank you. Okay. Um, application scenario 2. Had I skipped this one, by the way? Okay. So I think I had skipped this one. So we can also bundle up links into a single logical link between switches, between a switch and a stack, between a switch and a stack. So look at this. Look at this. This is a typical hierarchical layered network architecture. So we have the access switch here. The access switch, in order to provide backup, device redundancy is, is connected to more than one device or switch at the aggregation layer. So it's connected to this device and to this device. Are we together? But now we've used a technology called iStack or intelligent stack to combine these two physical switches into a single logical switch. Are we together? That's what iStack does. We're going to learn about it. But at this point, just understand that we've combined these two physical switches to act as a single logical switch. So when we do that, then we need to bundle up all these interfaces here. Are you seeing them? Into a single Ethernet trunk. Because now, logically, it's like they're connecting to a single switch. Is that clear? So between a switch and a stack. Okay, then heartbeat link. Okay, so not heartbeat. Heartbeat link of firewalls in hot standby mode. So if two firewalls are deployed in hot standby mode, can someone tell us what hot standby mode means? Hot standby mode. So the heartbeat link is used to detect the status of the peer device. So to prevent status detection errors caused by single interface or single link faults, you can create an Ethernet trunk and use it as the heartbeat link for status detection. So hot standby mode simply means that we are connected together and we are listening to each other. One of us is functioning, the other one is acting as backup. Are we together? So if this one that is working goes down, then the other one is what? Is activated. Are we together? But now, if we use a single link, to exchange information that is telling us that you are still up, if this link goes down and you also go down, are you seeing I'll never know that you've gone down and I won't be activated, right? Yeah. So to prevent that, at least use an Ethernet trunk that will provide a backup link. Is that clear? Yeah, so that is what we are saying there. Okay, so let's look at the configuration example. I want us to finish this quite fast so that now we can do the labs. So how to create an Ethernet trunk? Easy. You on system view, you use the command interface, then Eth Trunk, then the trunk ID. So for example, you are on S1, you use the command int Eth Trunk or just Eth, then the ID. For example, 1, like that. Then after that, you'll get into the Ethernet trunk S1 Eth Trunk 1 view. Then you can choose the mode. So mode can be LSCP or it can be load balance, manual load balance. So it can be that or it can be manual load balance. Manual load balance. Okay, allow me to say this, that LSCP mode is also commonly referred to as static LSCP mode. It's also referred to as static LSCP mode. I don't like this name a lot because most of the time in networking, when we refer to static, it means you're configuring manually. So I find this quite confusing, that here we are using a protocol to form the Ethernet trunk, and we are calling it static LSCP mode. Then the manual mode is also called manual load balancing mode. Load balancing mode. You need to understand this because in the exam they'll use static LSCP mode, and you might wonder, oh, what is that? Okay. So the other thing you need to configure is to add the interface to the Ethernet trunk. So adding an interface to an Eth trunk. So to do that, you go to the interface view, then you use the command Eth Trunk, then the trunk ID, for example, 1, then enter. So if you do that, then that particular interface will be added to the Ethernet trunk. So for example, you are on S1 and you are on G0/0/0. So that's how you add an interface to an Ethernet trunk. Okay. Then you can also add an interface on an Ethernet trunk when you are on the Ethernet trunk view. So Eth Trunk 1, we created Eth Trunk 1. So the command is trunk port, then int G0/0/1. So interface type, gigabit Ethernet, then the number. Oh, sorry. Yes, exactly. So that's how we add on the Ethernet trunk view. Okay, then enable interfaces at different rates to join the same Ethernet trunk. So remember we said that you should not add interfaces that are transmitting at different rates to the same Ethernet trunk. But if you want to enable that, you can use the command mixed rate link enable. So that's the command to do that. How do you configure a switch LSCP priority? Configure switch LSCP priority. So the command is S1 on system view. You do LSCP priority then the number, the priority. Remember, the default is 32,768. So if you give it a lower number, then it will be elected as the actor. So this is the priority value. So find out the maximum value for that. Okay. You can also configure LSCP priority on interface view. So the command is the same. The command is the same. Please note that when you configure this on interface view, you must have added that particular interface to the Ethernet trunk. If you've not added it to any Ethernet trunk, this command cannot work. Then you can configure the maximum number of active interfaces. So this is actually the correct. Earlier I had typed the wrong command. So let me just type it again. So if you're on S1 and you're on Eth Trunk 1, like that. So the command is max active link number. Link number. Link number and then a value. Maybe you want a maximum of 3. Read further about this, but I think the maximum number of physical interfaces you can add in an Ethernet trunk is 8. Is 8. 8. Okay. The next command specifies the minimum, the least active. So least active link number. This one, if you, for example, enter 2, it means that when the physical interfaces on the Ethernet trunk goes below 2, then the Ethernet trunk is disabled, torn down. So all links will be inactive. They can't forward data. Are we together? If you enter 3, if the active interfaces go below 3, the entire Ethernet trunk is torn down. So that is what that is used for. Okay, so an example of configuring an Eth trunk in manual mode. So in this particular case, we have switch 1 and switch 2. They are connected to the networks VLAN 10 and VLAN 20. So both of them are connected to VLAN 10 and VLAN 20. Switch 1 and switch 2 are connected through Ethernet links. To provide link redundancy and enhance transmission reliability, we want to configure an Ethernet trunk in manual mode between switch 1 and switch 2. So how to do that? You start by creating an Ethernet trunk using that command we just saw there. Then you add using the trunk port command, and you can use the range 001 to 002 to add these particular interfaces on the Ethernet trunk. Then after that, you can choose this as a trunk port, and then you allow VLAN 10 and VLAN 20 to pass through. So you'll do a similar configuration on switch number 2. Otherwise, we can use the same scenario to configure an Ethernet trunk, but on LSCP mode. So again, they're connected to VLAN 10 and 20, and they're connected through Ethernet links. They want to provide redundancy and enhance transmission reliability. We configure in LSCP mode. Then we manually adjust priority to make SW1, switch 1, the actor. Then set the maximum number of active interfaces to 2. So the other function, the other links will function as a link backup. So that is the requirement for this particular scenario. So how to do it? You create the Ethernet trunk using that command. Then use the command mod LSCP because we want to use LSCP. Then max active link number, we want 2. Then you add the respective links from 1 to 3 there to the Ethernet trunk. Then port link type trunk, because the interconnecting switches allow pass VLAN 10 and 20. Then you quit. Then you configure the LSCP priority. It can be any integer. So we are configuring that to 30,000, which is lower than the default 32,768. So definitely switch 1 will be elected as the actor. So that's how you do that. You're going to do it in the lab just now. You do the same on switch 2. So let's have an overview of iStack and CSS. So iStack in full is intelligent stack. Intelligent stack. So multiple iStack capable. Look here, they have to be iStack capable. So multiple iStack capable switches are connected using, they're connected using what? To form a logical switch that participates in data forwarding. So look at how that is done. So these links that are colored blue are what we are calling stacking cables, special kind of cable. So we have switch 1, switch 2, and switch 3. So we interconnect them in a ring topology. Are you seeing the ring topology? Are you seeing a ring? Because you've connected this one to this one, then this one to this one, then this one back to this one. So you connect them in a ring topology. So when you do that with a stacking cable, and these particular switches are iStack capable, then they are going to form a single logical switch. That single logical switch is what we call a stack. Okay, so that's one way in which you can combine physical switches to a single switch. The other way is by using the cluster switch system. Cluster switch system. 2 CSS capable switches are bundled into one logical switch. So normally you will connect them using a CSS link, cluster switch link, and you'll be able to form a single logical switch. Now this one is important. This one is important. This one is very important. So you can see that they're both doing the same thing. The difference is that iStack is configured on fixed switches, while modular switches use the cluster switch system. So don't forget that. Okay. So advantages of these technologies, advantages, awesome stuff here. So number one logical device simplifies the operation and maintenance and facilitate management. Please note this, that when you combine this to a single CSS, then you configure the CSS as if you're configuring a single switch. So you're not going to configure the 2 switches. You only configure one. So that's what we are saying. That one logical device simplifies operation and maintenance. Now, if a physical device fails, the other device can take over the forwarding and control functions, preventing a single point of failure. So you also provide backup. If one goes down in the stack or in the CSS, the others will still continue to work. Okay. So that is the advantages of CSS for iStack. Inter-device link aggregation is implemented. So you saw that one of the ways in which we could implement link aggregation was if we had such like an architecture like you're seeing here. So if you do that, if you do link aggregation, then no STP is going to be deployed because you can't have loops if you use that. Then all links in the Ethernet trunk are used when you use Ethernet trunk, and therefore the link usage is at 100% because you're not using STP to block some links. You've combined all of them into an Ethernet trunk. So some of the terms they might also use is, for example, many-to-one virtualization. Many-to-one virtualization, which is combining multiple physical switches or links into one logical switch or links. Then unified forwarding plane. A unified forwarding plane means that you're going to have a single routing table for all these combined switches or routers, switches really. So physical switches in a CSS use a unified forwarding plane. So they will share and synchronize forwarding information in real time. So then inter-device link aggregation, which is what we have talked about, the Eth Trunk. Links between physical switches are aggregated into a single Ethernet trunk interface to interconnect with downstream devices. Okay, so as you can see here, we've combined those two, because now we are connecting to a single. Before, this is how it looked like, and we needed to deploy STP. Right now, we already have a tree-like architecture, so we can't have a loop. But in this one, we had to deploy STP to prevent loops. Okay, so application, and this one is also very important and very exciting. Please understand this. When do you need to use iStack, for example? When do you need to use Ethernet trunks? Okay, so iStack, for example, you can use it to increase the port quantity. You can use it to increase the port quantity. So for example, you're having a lab like this one that has 25 machines. But the switch that you have, and they're using Ethernet cables, right? The switch that you have only provides 12 interfaces. So what you can do is maybe find another switch that has another 12 interfaces, then you combine them together into a single switch. And now you can be able to connect all the other devices in your lab. Are you getting the point? Yeah, so that is what we call extending the port quantity. Okay, so extending the bandwidth and implementing redundancy backup. So in order to increase the uplink bandwidth and add new switches to set up a stack and add multiple physical links to member switches. So first of all, here we can create an iStack. Then here we can use link aggregation in order to increase the bandwidth. So remember, these are access switches, and this is the interconnection between the access switch and the aggregation switch. So we can be able to combine them like that in order to increase and also provide reliability in terms of link bandwidth and link backup. So you're just being shown where in your network, as young network engineers, you're going to implement these technologies, which I think is very important. Previous notes did not have such case scenarios. Okay. Okay. So, of course, as we said earlier, when you implement, for example, CSS, then you're going to combine these two into a single logical switch, right? So once you do that, you also expected to use Ethernet trunks to bundle up these particular links, because now they are connecting to one switch, to one logical switch. So once you do that, you no longer need to deploy STP, as we have already said. So you don't need to deploy STP, MSTP, or another protocol that is called Virtual Router Redundancy Protocol. If you want to understand the function of this protocol, please watch my HCIP videos. So you don't need to deploy them. So this makes network configuration much simpler. Network configuration much simpler. And additionally, inter-device link aggregation will speed up network convergence and improve network reliability. Okay. So the recommended architecture. So here you're having an entire campus network. So where do you do what of all these things that we've learned? So this is very interesting. So I want you to take a few minutes before we go to the lab to discuss this. So where do you implement CSS? Where do you implement iStack? Where do you implement link aggregation? Where do you implement all those technologies we've learned on a campus network? So I want you to form groups, discuss this, then we do the lab. Otherwise, as you discuss this, also remember to discuss these questions on the quiz. Asanteni sana.